In this video, as part of the Signals and Systems series, we're going to talk about Fourier Series representation and Fourier Series coefficients. So this is a very interesting concept, but before we get into it, let's go ahead and make sure we are all on the same page. Some basic definitions relating to periodic signal. This Fourier series is only valid if the signal is periodic. So let's go ahead and start by some basic definition of what a periodic signal is. So the fundamental rule for a periodic signal is that if I have a function x of t, it has to be equal to x of t plus some number of seconds or some time later. This capital T is referred to as fundamental period or period. Let's call it fundamental period here, fundamental period. And so the most common signal we usually think about when we hear periodic signal is cosine of some general form of k omega 0 t that we usually write. We might even have a phase shift attached to it, but for now let's stick to this thing where k is just an integer that can go from minus infinity to infinity, and omega 0 is referred to as a frequency and is described in radians per second, and how it relates to fundamental period is going to be 2 pi over t. So omega 0 is a 2 pi over t, and this is referred to as the fundamental frequency. And this equation, of course, would work for all periodic signal. Just I wrote it for the cosine here, but you could go up here and say, okay, I can have this, then I'm going to have a linear frequency, which is 1 over t, and then I'm going to have a radian frequency, which is omega 0, for in this case omega 0 or omega, and that is equal to 2 pi over t. That's one way of writing it. If you don't like that, you can, or you have frequency, you can also write it like this, but the units are radian per second. So that's a little bit of a background on what a periodic signal is, and the fact that the cosine is one of the simplest one. And cosine and sine, just the sinusoidal, is a pretty important one for us. And if you remember, most of the electrical signals that get generated normally are of the form sinusoidal, or we usually represent a cosine because sine and cosine are almost the same thing. All they are pi over 2 shifted. There is a group of identities we refer to them as Euler's identity, and it's written as Euler's, but it's Euler's identity. And these guys are very useful, and if you have not are not very comfortable with it, I rarely recommend things to be memorized, but this you should really know by heart. And anytime you're looking at a equation that has anything to do with signal conversion from frequency to time domain, anything to do with the complex numbers, it's really good to have Euler's identity. The basic Euler's identity basically says cosine of alpha is equal to e to the j alpha plus e to the minus j alpha over 2. Sine, of course, would be sine of alpha, e to the j alpha plus or minus, I'm sorry, not plus and minus, just minus e to the minus j alpha divided by 2j. So these are some basic ways of converting from e to the j, from sine to the e to the j. And you may also see this written as plus minus j alpha, written as cosine of alpha plus or minus j sine of alpha. And again, these are collectively called Euler's identity, and it's recommended, I would highly recommend you kind of keep that in mind. And of course, the definition of periodicity is pretty basic. So now we come to this concept that we want to introduce, which we call Fourier series. And the Fourier series is pretty powerful because it basically says that I don't care what kind of a periodic signal you have. It could be a square wave, it could be a triangle wave, it could be, of course, a sinusoidal wave. It really doesn't matter. I can write it as a as the signal as components of it in frequency. And not only that, the components will only have non-zero value at discrete points, so they're going to be discrete, and their value, they will only have non-zero values at harmonics. And harmonics of a signal with a frequency omega 0 would be 1 omega 0, 2 omega 0, 3 omega 0. So let's say you have a square wave, and the square wave is of frequency 100. And that means this first harmonic is 100, the second harmonic is 200, third harmonic is 300. So Fourier series basically tells us that any signal you give me that is periodic, I can literally write it as a combination, as a sum of a bunch of frequencies added to each other times some coefficient. So this is kind of the foundation of Fourier series. K is going to go from minus infinity to infinity, a of k, e to the j, k omega 0 t. Again, remember k is the simply k is just an integer, and you can see that the integer in this sum goes from minus infinity to infinity, and then j is just saying this is a complex number basically, and a of k, this is referred to as the Fourier series coefficient. Okay, and and this equation is very important. You should and just to be complete, this is the fundamental frequency. That's basically if you have a signal that runs at 100 hertz and you want to convert it, omega 0 of that signal is 100 radian per second, or if it's in hertz, you multiply it by 2 pi. This equation is this x of t equal to that is referred to as the Fourier series synthesis equation. Very useful. Now let's kind of spend a little bit of time thinking about this. So that basically this summation, if I expand the summation out, it's going to start from minus infinity, but I'm not going to write all of them. But it's going to be like a of minus 2, you know, you're coming from minus k's minus, so this would be for k of equal to minus 2, e to the minus j omega 0 k, in this case actually the k is given, so it would be 2, better clean this up, let's start over, minus 2j 2 omega 0 k t, and then the next one is going to be a minus 1 e to the minus j1, we won't write, omega 0 t, and then a 0 is going to be e to the 0, which is basically 1, plus, and you can see a1 e to the j omega 0 t, plus a2 e to the j 2 omega 0 t, and on and on. So basically any signal we take, we're going to write it as this. Now what does this mean? This basically is taking our x of t and making a representation of it in frequency domain. So if you do an x-axis, let's say this is your x-axis, and here is what you represent if x of t, component of x of t in frequency domain. So that's what Fourier series allows us to do. So this could be omega, the variable, that's a variable omega, and then you can also represent it as k. So let's see what that means. So at 0, frequency 0, k is equal to 0. Or we can have it at omega 0. We can have a component at omega, omega 1. Omega 0. 1 omega 0, 2 omega 0 are called harmonic, right? And then you also have the negative side, so you have negative omega 0, negative 2 omega 0, okay? And k's, of course, would be 2, 1, 0, minus 1, minus 2. So what's the magnitude of x at this? Those would be basically a minus 2, a minus 1, a 0, a 1, whatever the values are. I'm not necessarily drawing them to be the same size. They could be whatever size they are. And a2, and on in this direction, on in this direction. Okay, so that's what it basically says. So if somebody comes up to you, now let's see if we kind of understand this. Let's say somebody comes up to you and say, I have a DC signal, x of t is equal to 2 volts or amps or whatever they say. So what is the frequency content of? You say, oh, look, this one doesn't have any e to the j stuff to it. It just must be a0. So you say, oh, that tells me that a0 is the only non-zero value of Fourier series, a Fourier series coefficient. Therefore, this must be, its frequency representation is just 2. Okay, so that was this. This is again a very important equation called Fourier series synthesis. And I won't go through the math here, but we simply can, with a little work, we can literally turn this around and try to find what a of k is in terms of x of k. It would be, so it's nice to be able to write this, but if somebody gives me an x of k, how can I find a of k, which is the Fourier coefficient? So that's our next task. Our next task is, how do we find Fourier series coefficients? Okay, and coefficients would be basically a of k's, right? So if I won't go through the math here, but the math is available in the text, feel free, and I would encourage you to go and walk through it. But basically the equation you come up with is called a of k is equal to 1 over t integral of this is a fancy way of saying go over a period. You can start anywhere, as long as you stop a period later, you're fine. And then it would be x of t times e to the minus jk omega 0 t dt, and that will find, and that's very useful. So you give me a signal, and if I want to write it as in this form of series of frequencies added together, all I have to do is use this equation, this integral, to find it. The name of this is Fourier series analysis equation. Okay, as we've talked about before, if we start an analysis equation, and as I mentioned before, when we name an equation, this is pretty darn important in our understanding of what's going on. Okay, so let's start applying this a little bit and try to understand how do you go one way or the other through examples. So we have this set of equation. If somebody gives us a of k and asks us to find this, we're going to use the Fourier series synthesis. If somebody gives us x of t and asks us to find what the content is at different frequencies, we'll use a of k equation, which is called the Fourier series analysis. So let's do an example. Let's say this is example. And this is an example. Somebody comes up to us and say, hey, you've got let's say they've given us they've given us something simple. So let's say they've given us a of 2 equal to 5, and then a of minus 1 is given to us. I'm sorry, this is a minus 2. A of 1 is given to us in 2. A of 0 is given to us as 5, and A1 as 2, A2 as minus 5, and that's good enough. And these are they say, okay, this is the non-zero Fourier series coefficients, and then the rest are 0. So we don't have to worry, the rest are 0. Okay, and they're saying, okay, these are given, these are the given, and they're asking us to find x of t. X of t. So okay, now I have two equations we just got introduced. One is analysis equation, the other one is synthesis equation. Oh, must be the synthesis, because if I have a of k, I want to find x of t. That's how I do it. Now, one of the things they should have given us is the and they have to tell us that what is the fundamental frequency of x of t. And let's say fundamental frequency of x of t is omega 0 equal to, I don't know, something simple like 100, so it doesn't get too confusing. And of course the units will be radian per second. So you say, that's fine. So that would be a summation of k going from minus infinity to infinity, and a of k e to the j k omega 0 t. That's basically the synthesis equation I'm copying from up here. And so, okay, well, I have all the non-zero a of k. It means all I have to do, I have to start at a minus 2 because the rest are 0, e to the minus j 2 omega, and then that's 200 t because omega 0 is 100, plus a minus 1 e to the minus j 100t plus a 0 plus a 1 e to the j 100t plus a 2 e to the j 200t, and there I have my signal. Now when we can you can go ahead and plug the values in and rearrange this a little bit. You will see that you've got 5e to the minus j 200t plus 5e to the j 200t, and then you got plus, I think it was one of these is a minus. I think this one is a minus. Okay, and then plus e, then a1 is 2, so I'd say 2e to the minus j 100t plus 2e to the j 100t plus a0 is 5, and we just leave it there. You can leave it there. You're done as far as the x of t is concerned, but you can also kind of look at that and say, oh, I kind of see this is minus 2j sine of 200t, if you like. If you don't, that's fine too. And then you say, oh, I can kind of see this one is actually 2 cosine of 100t plus 5. So it looks to me like this is a signal with the DC component, which we knew there was because we had an A0, and we've got a sine at 100 and a cosine at 100 and a sine at 200. You can do that. That's the next step. Again, we were applying, at this point, we're applying Euler's identity, right? And so that's an example of how you would use the synthesis equation. The other one, and this is a pretty famous one if you want to do the other way, an example of going the other way. This is kind of one of the standard one people use for showing Fourier series power, is they say, well, what if you had a square wave? So somebody gives you an x of t, and they say your x of t, it looks like this. Here is time, and what you got your signal doing is basically a square wave, comes up, down, and over, and up, and down. Again, it's periodic, okay? And the period is, you got 4 millisecond of a downtime from here to here, and let's say you've got about a 2 millisecond here, and at high is 5 volts. Okay, and this is your x of t. And they say, okay, having that, what is the Fourier series coefficient? You say, okay, now you're giving me x of t. You want me to find Fourier series Fourier series coefficient, which then I have to use the Fourier series analysis equation. And so what I'll do is go and say, okay, So that means I have to know what the period is. I have to know what the omega 0 is before I can start here. Period is really simple. Period is just t equal to 4 plus 2, which is 6. So the period is going to be 6 millisecond. Okay? And so if you want to work this out, you say, okay, omega 0 is going to be 2 pi over t, which is going to be basically the 6 millisecond on the bottom, and this gets a little bit ugly, but that's okay. So it's 2000 pi over 3 radian per second. Okay, so you say, okay, a of k, the equation is 1 over t. I have to integral over a period of x of t multiplied by e to the j k omega 0 t minus, has to be minus, dt. So this is the equation I'm getting to use. Okay. Now, so that's great. That's the equation. So how do I do? Well, what's the period? Period is 6, but so that's fine. So I've got 1 over 6 times 10 to the minus 3. Now, I'm going to integrate from here to here. Let me use a different color. I'm going to integrate from here to here for one period, but during this period is 0, so all I do is go from 0 to 2 times 10 to the minus 3. My x of t is just simply 5, so that's my x of t, and I just simply write e to the minus j k omega. Oh, and we know what the omega 0 is, but why not? Let's not put it in. dt t. Pretty simple integral. At this point, I'm hoping that you can all do the integral, which is going to be based. I'll just do the next step. A of k is going to be basically 1 over 6 times 10 to the minus 3. The 5, we're just going to bring it out. And then the bottom is going to be minus jk omega 0 and e to the minus jk omega 0 t. And we're going to integrate this from 0 to 2 times 10 to the minus 3. Which makes a of k be equal to, just plug the values in, and that's your a of k. And if somebody wants to find out, let's say, what is the value at 0, they just set the k equal to 0, and that tells them, if they want to know what the a is, a of 1, what a of 1 is, all they do is they set k equal to 1, and that tells them what the value is at omega 0. So that's, you give the frequency spectrum of that. It's a little longer video than we normally do, but I felt like it was really important for us to introduce some fundamental concepts, this fundamental concept, which was what is a periodic system, remind you that Euler identities are really important, remind you that cosine is a very simple periodic, one of the most basic fundamental periodic signal, very useful in electrical engineering. Almost all of our signals are sine or cosine. Then we talked about Fourier series, which allows us to write x of t in terms of its frequency component at the harmonics, omega 0, 2 omega 0, on and on. And then if you wanted to find out what the value at every frequency, every harmonic is, simply calculate the a of k using the analysis equation. Hope that's been helpful, and look forward to having you on the future videos.